The sum S sub n of the first n terms of an infinite series is what we call a partial sum. The partial sums of an infinite geometric series may actually approach a limiting value, and that's what we're going to be doing in this lesson. Now, just as an example, consider the infinite geometric series 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and that continues on indefinitely, so we have an infinite series. Find and graph the partial sum S sub n for n equals 1, n equals 2, n equals 3, 4, and 5. And then we're going to describe what happens as our sum approaches, where our sum approaches as n increases. So for example, the sum of the first term, well, the first term is just 1/2, so when you add just 1/2, you get 1/2. And we're going to sum up the first two terms. In that case, it'll look like 1/2 plus 1/4. And when you add those together, you get 3/4, which is 0.75. So here you have 0.5, 0.75. If we sum up the first three terms, we'll have 1/2 plus 1/4 plus 1/8. And when you add those together, you get 0.88. And then S sub 4, we're going to sum up the first four terms of this infinite series. 1/2 plus 1/4 plus 1/8 plus 1/16. And that'll give us approximately, plugging in the calculator, 0.94. And then summing up the first five terms. And that approximately is 0.97. So here, as we sum up our terms, you'll notice that the sum is increasing, but it's approaching a limiting value, and that limiting value actually appears to be 1. So I'm going to plot those points. So we have 0, let me zoom in a little bit. So on our x-axis, that's going to be technically your n value, so what term we're at, and then we have our S sub n value, whatever we happen to have. So our first term is 1/2. So plotting that, we have 1, 1/2, and then our second term was 0.75, and then 0.88. Now remember, we are going by halves on our y-axis. 0.94 and 0.97, and I'm actually not going to connect them because this is what we call discrete data, so you can't have, if I were to connect it with a line segment or any kind of curve, that would indicate that we could have an n value anywhere between 1 and 2, and we can't have a term that's in between 1 and 2, or we'll have a fraction. You don't have a 1.5 term, so we don't connect them. It's, again, discrete data. So this is what the graph would look like. And then it says to describe what's happening. So as n approaches infinity, so as the terms get bigger and bigger and we start adding them, the sum in this instance will approach a limiting value of 1. The sum of an infinite geometric series with the first term a sub 1 and a common ratio, so we're only talking about geometric ratios, so that's why we have a common ratio, is given, and there's an actual formula for this, and it's going to look like this. S equals a sub 1, that's the first term in the series, divided by 1 minus r. Now the next part is pretty important. You want to make sure that you circle it. Given that the absolute value of the ratio is less than 1. So if the absolute value of the ratio is greater than 1, then we say that the series has no sum. So you actually cannot sum it up. So the ratio can't be bigger than 1. So make sure you keep that in mind when we do these problems. For number 2, Here we have an infinite series. We know it's infinite because there's an infinity along the top, so we're going to sum these up to infinity. This is already in geometric form, so 3 is the first term of your series, and the ratio in this case is 1/4. So I'm just going to list that out. A sub 1 is equal to 3. You could list out a first couple if you like, but I already see that this is in that form. And the ratio in this case is 1/4. So in fact, because our ratio is less than 1, we do have a sum here, so we can use the formula. So S equals 3 divided by, I'm just plugging this into the formula that's up above, and then 1 minus 1/4. Here we have a complex fraction, so I'm going to clear out my complex fraction. Looking at my fractions, I have a common denominator of 4. So I'm going to multiply every term by 4. Make sure that you multiply the 1 down in the bottom by 4 as well. And that gives us 12 in the numerator. And then 4 minus 1 in the denominator. So 12 divided by 3 is 4. So the sum of this infinite geometric series would be 4. So that's your limiting value. Number 3. This one we have to take a little bit of work to figure out what the ratio is. So first of all, it's pretty easy to find a sub 1. So a sub 1 is negative 1/2. And if you look at the ratio, they are multiplying by negative 1/2 to get the next term. So negative 1/2 times negative 1/2, when you multiply those, you get 1/4. You multiply 1/4 times negative 1/2, you'll end up with negative 1/8. So our ratio here is negative 1/2. And the absolute value of negative 1/2 is less than 1, so our sum is actually exists in this one. So I'm going to use the formula. Negative 1/2 is the first term that's in the numerator, and then 1 minus the ratio, which is negative 1/2. To clear the complex fraction, our common denominator is 2, so I'm going to multiply each of these terms by 2. That gives you negative 1 in the numerator, and 2 plus 1 in the denominator, so we get a sum of negative 1/3. And for this last problem, write the repeating decimal as a fraction. Now we're going to do this without a calculator in lowest terms. And here we have the repeating decimal 0.131313. So the portion that's actually repeating is the 1/3. So I'm going to break this down a little bit, probably something that you wouldn't have thought of, but again, you'll see it hopefully after I write it down. So I'm going to break this down into 13 because that's the part that's repeating. And then that I'm going to multiply by 0.01, and that'll give you the first 0.13. And then I'm going to add on 13 times 0.01 squared. That'll give you the second 13. Plus 13 times 0.01 cubed. Again, that'll give you the third one. And then that'll continue indefinitely. So the reason that I did this was because this will give you your first term. So if I take a look at right here, this will be my a sub 1. And we have our common ratio of 0.01. Because to get to this next term, I had to multiply by 0.01. 0.01 times 0.01 times itself will give you 0.01 squared. If you multiply this term by another 0.01, you'll get 0.01 cubed. So that's your common ratio. So again, this ratio is less than 1, so we do have, we can use that formula. So it'll be S equals a sub 1, which is 13 times 0.01, divided by 1 minus 0.01. So when I multiply through in that numerator, you'll get 0.13. And in the denominator, you'll end up with 99 hundredths. And multiplying both the top and bottom by 100 to clear out the decimal, we end up with 13 divided by 99, which cannot be simplified any further. So that's a repeating decimal as a fraction is 13 divided by 99. Now I'm going to do a quick little example, another example that's pretty similar down below here with a different repeating decimal. So just as another example, suppose we had 0.132, and this continues indefinitely. What we'll do here is we're going to break this one down into, I'm just going to notate what the repeating part is. So this would be 132 times. Now this would actually be 0.001 because the repeating decimal in this case would be 0.132. So I need to make sure that I multiply that by 0.001, which is 1/1000th. I'm going to add on 132 times 0.001 squared, multiplying the first term by that ratio. 132 times 0.001 cubed, and then again that goes on indefinitely. So plugging this into the formula, the first term in this case would be 132 times 0.001, and then 1 minus the ratio, which is 0.001. And then this gives us 132.132 over 0.9999, multiplying in this case by 1000 to clear out the decimal. You get 132 divided by 999. And then this fraction actually can be simplified by dividing by 3. So when you divide 132 by 3, you get 44. And 999 divided by 3 is 333. So this would be a fraction in lowest terms as whatever the repeating decimal was, the 0.132, 132, 132, 132 indefinitely.